Good morning, everyone. My name is Eric Romo. I am the DS23 tutor for business statistics here at Fresno City College. Today we're going to be talking about binomial experiments. So, with a binomial experiment or a binomial distribution, we are working with an experiment that has to follow a certain four rules. And these four rules state that the experiment consists of n identical trials. Each trial results in a success or failure. The probability of success remains constant, and so does the failure. And also that the rate of failure is denoted as Q and is the complement of the probability of success. And the trials are independent of each other, which means they have nothing to do with each other. Alright, so let's take a moment to dissect what was being said here. So, the experiment consists of n identical trials, which means that every trial will be identical in nature, which means that the methods of obtaining the probability will not change. Each trial results in a success or failure, which means is that we have a probability of success denoted as P, and we have a probability of failure. So, what that is trying to say is that there is a probability of success that we are looking for. However, that may result in a failure if it does not occur. Because probability, we know, it's probable. It's not guaranteed that that event will occur. With a probability of success that remains constant, and so does the failure, is important because that comes back to this first one, consists of n identical trials. They don't change at any point, and they should not. So that ties into this fourth one, that the trials are independent, which means they have nothing to do with each other. So once one trial is made, it will not affect the probability of the next trial at all. So we're given this equation right here, and to read it states that a binomial random variable and the probability of obtaining x successes in n trials is ncx, which this states a combination, okay, because we're accounting for all the possible probability of obtaining those x successes in this n total sample space. The probability times the probability of success to the trial power multiplied by the rate of failure to the n minus x. So the sample space minus x, which was right here. And so with each one of these, n is our sample space, x is the trials of the event, p is the probability of success, and q is the probability of failure, with q is equals 1 minus p. So let's go ahead and put this into practice, okay? A hospital records show that 75% of patients diagnosed with a necrotic disease will die. Wow, morbid problem already. 6 randomly selected patients are chosen. What is the probability that 4 die? Alright, so first thing I need to know is, what is my sample space? That's the first question we always need to ask in statistics. What is the sample space? So I know that n, okay, is our sample size. So it said that 6 patients are randomly selected. So that is going to actually be my sample space. Now my x, okay, the trials of the event. It says right here, what is the probability that 4 die? So that is my success trials. I want to know successfully how many 4 will die. Now I know that sounds a little weird. We don't want anyone to die, but that is in statistical notation and what we're looking for our success. Because right here, 75% of patients diagnosed with a necrotic disease will die. So if I'm looking for someone who will die, this fits that condition. So that is our trials of success. So I need to look for my probability of success, which we said before, which was 75. Or I can put it as 3/4. Or I can even put it as 0.75. And my Q is equal to 1 minus P. So if P is equal to 0.75, 75%, then 1 minus P must be 1/4 or 0.25. Now let's notice something, okay? One of the basic rules of probability states that probability must be in between 0 to 1. And also, the summation of a probability distribution must equal 1. So, we just demonstrated this concept. If I added 0.75 and 0.25, I get 1. And also, it's between 0 to 1. So these do fit the basic concepts of probability. So now that I have all of my variables that I need to plug into my equation, I can do that. So 6C4 multiplied by 0.75. I'm just following this equation right here. So my probability of success was 0.75 to the x. So that's going to go right here, multiplied by my rate of failure. Rate of failure is 0.25. N minus x. So I have n, which is 6, minus x, which is 4, which must mean it's equal to 2. Now let's take a look at something right now. Before we do any calculations, is that I notice something. 0.75 plus 0.25 is equal to 1. So I know that so far I'm good with my probabilities of success and failure. Also, 4 plus 2 is equal to 6. So that's another way that you can know that you're doing this right, is if this power plus this power equals your sample space. So let's go ahead and calculate what these values are. I don't have a NCR function on my computer calculator, so I'm going to enter it into this online calculator right here. It says that value right here, NCR, is equal to 15. So I'm going to write that right here. So 15, okay, multiplied. Let's figure out what 0.75 to the 4th is. Let's open that calculator. What the heck? Oh. So 0.75 to the 4th power. Okay, I get this long running decimal, so I'm going to keep it like that for a second. And it says for the next one, it's 0.25 to the 2nd. So I'm going to multiply this number in parentheses, 0.25. I'm going to square that. Okay, so I get this long running decimal. Okay. Now all I've done is I've just simply calculated what these are. So multiply 15 by that long running decimal in my calculator. So I'm going to now put multiplied by 15. Okay, so my probability here is 0.2966. I'm going to just round to the 4 decimal places. So 0.2966. And let's go ahead and... So what was this number? I can write this in. Right here for you guys. 0.01977539065. Okay, so this bottom number, that 0.2966, is actually the probability that 4 out of 6 patients will die. And that's all there is to it.